Okay, if you take a look at this hidden Markov model, and if you look at multiple sequence elements, some states will not be there in the profile hidden Markov model that you're going to be building. For example, I can direct by looking at the second conserved sites, I can see that all the sequences have the second conserved site. They have emitted some symbol at the second match state. What does this mean? It means that uh, the delete to state is never visited by any of these. So if you're not using pseudo counts, pseudo transitions, it means that in the profile hidden Markov model that you're building, you're not going to have the delete to state. Or similarly, delete for. The delete for state that is shown here in this template, do you have that? Will you have that in your profile hidden Markov model that you built? None of the sequences that you have in the multiple sequence alignment has visited the delete for state, because they have all emitted something at M4, meaning that delete 4 is not visited. So delete 2 and delete 4, for example, is not going to be in the final profile hidden Markov model that you built, since you're not using pseudo transitions. That's again indicated here. So it also says if a certain, you may omit. So here, some insert delete state if the profile hidden Markov model, of the profile hidden Markov model, if they are not visited by any of these 8 sequences. So I can, so this is like a hint for you. Delete 2 and delete 4 will not be there. So the Viterbi table, I don't want to check all the remaining states which are going to be there, but how many states I have here in total? 2. So there are 12 here, 14. So 14 states, but I know 2 of them are going to be missing for certain. So there will be at most 12 states. So you're going to be filling a table of 12 by 7, including the empty string. There will be 7 columns here, and there will be at most 12 rows in the each one for each state. So you will be filling in a very large table. And if you're going to do it by hand, you can still do it by hand using a calculator. It will take a lot of time. That's why it's given as an assignment. I will not ask a midterm question that is as long as this, especially for the Viterbi case and this many states. But as a homework, I think it will help you to understand how the Viterbi works, how we build the profile hidden Markov model, and compute the transition probabilities. All right, so that's your second assignment. Any questions about these? Today I'm going to quickly remind how the Viterbi algorithm worked like. Although we worked on an example in the sample midterm exam, you see the main thing is that the recurrence relation tells us that the probability of the best path that ends at a state and the last observed action, the last observed symbol is xi. The probability of that best path is equal to the emission probability of that xi at mu. If it's a match state, we must have emitted the ith character, that is the last character that is observed. It has to be observed at match state u, if this is the state we're currently in, right? So we have to multiply it with the emission probability no matter where we came to that match state from. We may have come to that match state from the previous match state, or from the previous insert state, or from the previous delete state. So these are the possible paths, possible states that can precede match state u, and we consider all those probabilities that end at those states, the probability of the best path that ends at that previous state. If somebody gave these to you, it will be just a matter of comparing these 3 values to find the best path that ends at mu. So the problem is that we don't know these things yet. This is what dynamic programming is about, okay? So it's a recurrence relation. We don't know the values of these smaller instances yet, but nevertheless, it's a smaller instance of this problem because we are looking at a previous match state, previous insert state. It will get us at the end to the begin state where we don't use any recurrence relation at all. The probability of beginning at the begin state but empty string is going to be 1.0. This is where we will begin. So each of these recurrence relations, they have to have base case where we don't use the recurrence anymore. Otherwise, we would have to be stuck in an infinite loop if you're always recursively calling something. Okay, just like mathematical induction. Actually, in induction, you start with some base case, and you have this inductive hypothesis, which is like a recurrence relation. All right. So you have to multiply these whatever probabilities you have here for these best paths, these three possible paths that states that can precede mu. You also multiply it with the transition from that state to mu. Okay, so these transition probabilities should be multiplied, and this recurrence relation basically tells you how you fill a table, because filling in a table, you reuse some of the entities that are computed here, may be used again by other recurrences. So putting those values in a table makes this a dynamic programming solution, and you avoid computing them over and over again by putting these values in a table. A couple of things I want to mention about Viterbi is that there are some variations, like instead of multiplying the probabilities directly, as you can imagine, for very long sequences and for very long sequences, we will be multiplying lots of things. Imagine we have a protein sequence which is 30 nucleotides long, even like 300 nucleotides long, and we try to align it a family of a very long protein sequence. So multiplying all those 300 plus numbers, because when I have 300 sequences, I will be multiplying 300 emission probabilities and 300 transition probabilities between those states. So at least 600 of those numbers are going to be multiplied, and each of these numbers are between 0 and 1. Which means that as you multiply them one after another, the numbers are going to get smaller and smaller and smaller, closer to 0. You will at some point, your double precision practically, even if you're using double precision in whatever programming language you're using, it's not going to be sufficient to represent the numbers that small. So one way to avoid these small numbers is to convert these multiplication of these numbers that are smaller than 0.1 to the log of these numbers. Okay, so here is a variation. This is just a simple mathematical trick. Okay, because the multiplication of these two numbers, if you take the logarithm of that, it becomes the summation of the logarithms of the individual things. So multiplication of this v times t, if you take the logarithm of these two things, it becomes the multiplications turn into logarithms, and these small numbers that we have here, they become some negative numbers. So the logarithm of a number between 0 and 1 becomes a negative number, but if you're the larger the number, the logarithm is going to be still larger than, you can still use the max term. And at the end, you will be computing not the actual probability, but the logarithm of that probability that you're looking for. So whatever you have here, you can at the end take it e to the power to this number if you're wondering what the actual probability is. Most of the time, you don't worry about the actual probability because it's a very small number anyway. You're just interested in what is the best path among the profile-hidden Markov model that produced this. Or if we have probabilities from this profile-hidden Markov model, we compare it to another probability from a different profile-hidden Markov model for a different family. So we compare these logs of probabilities are directly comparable. So you may leave it like this, and it allows you, instead of multiplying very small numbers and getting smaller and closer to 0, you are going to have a negative number, which is going to get larger, and it's again going to get smaller, but 10 to the minus 7, 10 to the minus 10, 10 to the minus 15. It's going to get 10, and if it's 10 to the minus 15, it means that your number is like becoming minus 7, minus 10, minus 15. So it's going to get, the negative value is going to get smaller and smaller, but it's going to still remain manageable. And the multiplications you have here are converted to summations with this mathematical trick, and you're able to compute these very small probabilities as just like we do in scientific notation. So writing the probabilities just like as in the assignment, where was the assignment? So just like as in the assignment, instead of representing it like this, if you represent it like this, you're just maintaining this -7 point something. It will be, your number will be -7 point something. As the number gets smaller, it's going to be -10 point something, -15 point something, but there it may be as close as possible to 0. You will still be able to represent it if you take the logarithm of that number. So this is, as I said, as just one note that I want to mention. If I ask questions in the exam or also in the assignment, as you have seen, I didn't ask you to take the logarithms, but just know that practically in real applications, this is how they implement profile hidden Markov models. They take the logarithm of those probabilities and maintain the summation of these logarithms as we compute the best path along the profile hidden Markov model. And the other thing is, sometimes we just wonder about not the best path, but what is the overall probability of this profile hidden Markov model to produce that sequence. In that case, this recurrence relation just changes. We have to consider summation over all possible paths that produce that sequence. So we just change this max term to a sum term. If we sum up all these probabilities, okay, then it becomes the probability of all possible paths that produce this sequence. And the summation, turning this to summation, you will be computing, you will be asking this question. Where is that question? Yeah, the second question. Scoring a sequence against the profile hidden Markov model. So Viterbi solves this first part, given a query sequence, find the most probable path. Find a single path along the profile hidden Markov model that will produce our query sequence, the most likely path that will produce our sequence. By using the max operator, we find this. So the probability that the given query sequence is emitted by that hidden Markov model, actually, if you think about that, there may be millions of different paths that could have produced the same sequence. So if we ask what is the probability that this sequence is emitted by this profile hidden Markov model, we have to sum all those different possible ways that sequence is emitted from that. So by converting this max operation to a sum operation, we can compute the sum over all possible paths that can produce this. So it's a simple way of turning these max says to sum. So here how it's written as a sum of these things. And in this case, the logarithm is not going to work. So since we're summing these probabilities, we may as well leave it as the summation of these probabilities. Since although these will be small, summing these multiple probabilities is not going to be as small as the Viterbi algorithm. It will still be small, but as you can see, when you take the logarithm of these things, you cannot just sum the logarithms directly. The logarithm of this is not equal to the summation of the logarithms, so you cannot apply it like that. But forgetting about that logarithm trick, the only difference we have done here, as you can see, is instead of taking the max term, we have summed up all the possible probabilities of the possible preceding states that lead to MU. And the application of these hidden Markov models, by the way, do you have any questions up to this point? So this is now, this concludes our discussion on the Viterbi algorithm and the hidden Markov models. I'm going to be finishing up soon. So we are going to start talking about multiple sequence alignment algorithms. So if you have any questions about the profile hidden Markov models, I will be happy to answer them. You can also ask later when you're working on the assignment. I'm sure you're going to have questions when you're working on the assignment. Please feel free to send an email to me. All right. So the way profile hidden Markov models again practically uses, if we have seen that superfamily database, right? Superfamily database profile hidden Markov model. If you take a look at the supfam.org, superfamily 2. It's a database of structural and functional annotation for all proteins and genomes. It's based on a collection of hidden Markov models. So we have a family, a function, a protein function, and we find orthologs of orthologous protein sequences that have that same function. The first step we can do is we can build the Markov models of those after we multiply align those things. So we can actually use the techniques we have learned in the last week to build this database of profile hidden Markov models. So they actually do not build profile hidden Markov models for the entire protein sequences. They actually chop these protein sequences into smaller pieces, which we call domains. So a protein domain is a subsequence of a protein sequence, which is responsible for some function. Okay, for example, DNA binding domain, phosphate binding domain, or basically if a protein sequence have that domain that you can consider as I said, a subsequence inside a longer protein sequence, it's mostly indicating that that protein has that function, and use that part of the protein is used to perform that function. And there is a nice database called SCOPE. We are going to take a look at this when we talk about protein structures. So it's functional for, it says for all proteins and genomes, but the hidden Markov models are built actually for those protein sequences whose structure are known. So SCOPE is a database which structural classification of proteins. So the protein domains are, their shapes are taken into account in SCOPE, and they are hierarchically categorized, organized in a nice database. And superfamily level contains protein sequences which have some sequence similarity and lots of structural similarity. So there are superfamilies of protein domains here. By using that, they build lots of superfamily groups together domains which have an evolutionary relationship. So they know that these are orthologous proteins, these domains. These domain sequences are orthologous to each other. They built the Markov models about for those. Now, one possible use of the superfamily 2 database is that imagine you have a new protein sequence, and you may want to know whether it contains certain domains. If your protein sequence contains certain known domains in it, it may be very well used to predict the function of this new protein sequence. So we can use superfamily 2 database to align our protein sequence or parts of it. We can get subsequences from our superfamily 2 database and try to align by using the Viterbi algorithm or by using this forward-backward procedure, which sums all the possible probabilities. We can align our query protein against each one of those profile hidden Markov models for each of these domains that are in this database. The one which gives the highest probability probably and may also we may have a probability threshold too. It may be an indication of our new protein sequence having that same domain that is in this database. So this is how we can compare a new sequence against these profile hidden Markov models and find. So you can actually paste your sequence, your new protein sequence, you can paste here in FASTA format, and then it will be compared against these profile hidden Markov models. There are papers, studies that show that this is more accurate in terms of function identification, for example, for compared to BLAST, because BLAST is just pairwise search. Here in profile hidden Markov models, it takes into account, if I have a family of a protein, it takes into account some important parts, the characteristics of that domain into account. It's not like one-to-one pairwise sequence alignment. We're comparing a single sequence against a profile, which is like something probabilistic, and it can give you a better indication of what function our sequence can have. All right, so this is something if you want to take a look at this, you may learn more by reading the paper about the superfamily. So here's the paper, a couple of papers I think the first paper is a 2001 paper. Assignment of homology to genome sequences using a library of hidden Markov models that represent all proteins of known structure. Yeah, so this is the first paper that introduced this superfamily database. So you can, if you're interested more about this, you can read their paper and you'll see they probably use similar profile hidden Markov model templates that we have used. So if you look at the full text, for example, of this one, so this is the original article that appeared in 2001 in Journal of Molecular Biology. So if I zoom in on this, or if you take a quick skim through of this, it talks about different parameters of the database, and it's about structure and how they built, some statistics about the database that they built. They talk about they talked about the hidden Markov model library. They have validation, but they don't talk. Maybe if you read the methods section, you'll learn more about what kind of a template structure or how they built those hidden Markov models will be clearly described in this paper. All right, so this is how we can use profile hidden Markov models to search a new sequence against the database. And the construction of the hidden Markov model for a new protein family, we can first use multiple sequence alignment first, then build the profile hidden Markov model by using the technique we learned in this class. There is also a method without actually using multiple sequence alignment. Without aligning those sequences in the protein family, but we can train a profile hidden Markov model by using the Baum-Welch algorithm, which we didn't see in this class. So it allows you, just like in speech processing, we can train a profile hidden Markov model. Again, we have to make certain assumptions. For example, how many conserved sites are we going to have? We have to make certain assumptions on these. We may try different numbers of conserved sites, build different models for each of them, and it will, at the end, we'll learn these transition probabilities. It's going to learn in such a way that the probability of emitting each of the sequences in your family is going to be as large as possible from this trained profile hidden Markov model. Yeah, we have to make these decisions. So we are not going to cover this algorithm. We will assume that first we have first we are given a multiple sequence alignment of those things, and that's what we are going to see next. Okay, we are going to see. So there are different profile hidden Markov model tools that are available, and now we are going to see how that multiple sequence alignment can be performed when we have more than two sequences. And this problem itself is a difficult problem, but there are heuristics which provide very nice results, like clustable omega is one such algorithm, which by using pairwise sequence alignments build a multiple alignment of those sequences, and we are going to see these heuristics in the following weeks. All right. By the way, in the midterm exam, you're going to be responsible all the way. We are going to cover multiple alignment algorithms next week. We are going to finish. So the midterm exam is going to be on the 3rd of May in class on Monday morning. It's going to be 2 hours exam. I'm going to post an announcement about this soon on OttoClass. But it will also include the multiple alignment algorithms. It will be until the end of this set of slides. So we are going to finish multiple sequence alignment. I will start today, and we are going to, I plan to finish at least part of it, or maybe all of it next week. That's my plan. And it's going to be included in the midterm exam. All right. So, in the midterm exam, which is going to be on OttoClass, there may be some text or essay type questions that you may have to enter, but you will be basically using OttoClass to enter your answers. Some of them will be numerical questions, and you will not need to turn on your camera you may leave your cameras off, so it will be basically open book exam. You may refer to these things. So it will be like an open book exam, but numerical questions that I'm going to provide, some of them may be randomized. So you may get different questions. Each of you will get different numerical questions. But the essay type questions, everybody's going to get the same. And as I said, it's going to be like an open book type of exam that we are going to have on 3rd of May, Monday, in class, in the class hour actually. All right, so let's go ahead and start talking about multiple alignment problem. So why is it difficult, and what kind of algorithms we have? It's a difficult problem, but we still have techniques that provide good results. So they may not always guarantee the best way to align these sequences, especially when your sequences that you're aligning, if they are not highly similar to each other, aligning them multiply is a challenge. But multiple alignment is one of the most essential tools in molecular biology because most of the time we have more than one sequence when we're analyzing things. The same protein may occur in multiple places. For example, think about this COVID case, the virus strain. There are different mutations, like we have these different versions, the South African mutation, the English mutation. So there may be different cases. Each of since the virus mutates so frequently, we have all these different virus strains. If these genomes of these different strains are available publicly, one way to do is just put them on, align all these different strains on top of each other to see which parts are common in all of them, which parts are different. Okay, so multiple alignment algorithms are used in this regard, for example. So one goal, maybe you may want to design a diagnostic kit which is going to detect all these strains, whether you have the English strain or or you may want to develop a vaccine which is going to be effective in all of them. So after multiple alignment, you may want to see which sequences are common in all these different virus strains, which parts are different, and target those common regions maybe when you're developing a vaccine. So multiple sequence alignment is really an essential tool. And as I said, most of the time we have multiple sequences that we analyze. And in 1980s, they were constructed by hand. So when they were building these Blossom 62 pHMM matrices, they had to do multiple alignment. And what's a multiple sequence alignment? We are given K sequences. So unlike pairwise sequence alignment, where K is always 2, pairwise sequence alignment, we have an arbitrary number of sequences. The catch in multiple sequence alignment is that the dynamic programming solution we have for pairwise sequence alignment, which is polynomial time, it actually becomes exponential in K. Okay, so which means that as K gets larger, if, for example, when K is 20, you will have a running time the computational complexity of the dynamic programming solution grows exponentially with K. The couple of slides show, which means that the next couple of slides is going to show why it's exponential. Because each time one quick answer is that for 3 sequences, for example, you will need to fill a table which is 3-dimensional, then 4-dimensional, 5-dimensional table. And you have a 5-dimensional table of n times n times n times n. As you can see, you're going to have n to the power k entries in the table. If you are trying to align k sequences, you're going to be trying to fill a k-dimensional table. When k is 2, it's a 2-dimensional table. It's quadratic, it's doable. But when k is equal to 10, practically it will not be possible to use the dynamic programming. Even for values of k is equal to 4, for example, an algorithm which is n to the 4 algorithm, when the sequence length n is large, may become impractical when you have even k is equal to 4. Okay, and most of the time we are aligning like 10s, 10 sequences, 20 sequences, or even more, which makes dynamic programming solution not usable. Practically, we will not be using this. And what makes this more complex is that multiple sequence element, we can put think about the combinatorial ways you can put different gaps in different places. So even if I tell you that in this column, for example, I have 4 gaps, for example, the way you can put these 4 gaps among these 8 sequences is 8 choose 4. So combinatorially, each of the decisions you make are they explode exponentially. That's why it becomes your solution space becomes really huge. But what we try to do, what do we do multiple sequence alignment for? We again find regions. So here the following stuff. We, for example, find certain conserved sites which are common in all of our sequences. We can find some regions, conserved regions, which are common to at least, for example, half of the sequences we analyze. We may find some patterns which may look a non-conserved region. The position 1 and position 3, they are all hydrophobic residues. It may be some physiochemical pattern that we find about this domain. This may be a protein domain that we're looking for, that may be in the middle of some longer protein sequence, and it may indicate something. Okay, so multiple sequence alignment is basically just extend your pairwise sequence alignment to multiple of them, and you can put gaps in any of those. You can have matches, mismatches in a single column. For example, the first and second sequence is a match. This S is a match in that, but S and G is a mismatch. So there are, if you have K sequences in your multiple sequence alignment, there are K choose 2. Each pair of these sequences you see here is a matching between them. S and G mismatch, S and G mismatch, G and D mismatch, G and G match. So you have matches and mismatches. So every pair of sequences in that column gives you something. And this is how we usually compute the score of this multiple sequence alignment. It's by sum of pairs score. You can look at all pairs and figure that out. Now, one thing we may ask is that when we are given a multiple sequence alignment like this, it immediately induces, the multiple sequence alignment induces pairwise alignments, right? There are actually, what you see here is that there are 1, 2, 3, 4, how many? 8? I have 8 sequences here. There are 8 choose 2. 8 choose 2, which is 8 times 7 divided by 2. Okay, or yeah, and 8 factorial divided by 2 factorial times 6 factorial. 6 factorial cancels out, so I am left at this. 28, right? There are, so here in this slide, you see 28 induced pairwise alignments between the first sequence and the second sequence, first sequence and the third sequence, first and fourth, second and third, second and fourth. So there are 28 pairwise alignments here induced by this. Now, if there are 28, the question that I want to ask is, if somebody gives you those 28 pairwise alignments, by using them, can you build this? The thing is that if you look at these pairwise alignments induced by this multiple sequence alignment, some of the decisions, if this is an optimal multiple sequence alignment, some of the decisions we made for the pairs may be not optimal if you consider just these 2 pairs. So the multiple sequence alignment, when we are doing the multiple sequence alignment, we have information about the entire 8 sequences. When we make decisions, if we are doing an optimal way of doing this multiple sequence alignment, we are using all the evidence about all those 8 sequences. And the decisions we make are not pairwise, may not be pairwise optimal. What I'm saying is that if you look at the induced pairwise alignment between 2 sequences that are here, And if you take a look at the actual pairwise alignment, optimum pairwise alignment between these two, they may not be equal to each other. Okay, so this means that the pairwise alignment may not appear as is in the multiple sequence alignment. And sometimes the pairwise, those 28 pairwise alignments you have, combining them together into a single multiple sequence alignment is challenging because some information in those 28 multiple sequence alignments, pairwise alignments, may be conflicting with each other. One such conflict I want to directly show you is the one example that is in the textbook, which is this. Okay, this is an extreme case, an extreme example. It's a multiple sequence element of 3 sequences. Okay, AAA, TTT, TTT, GGG, and this AAA, GGG. So when you look at these pairwise alignments, so these 3 sequences, I have these 3 sequences at the corners of this triangle. So I have these sequences, and each triangle edge actually shows the pairwise, the optimum pairwise alignment of these two things. Okay, so the optimum way, optimum pairwise alignment of these two sequences are given here. So T's are aligned like this, A's are aligned like this. So when you have such a pairwise alignments, you may actually, since A comes before T, then comes G, you may observe the same thing. A comes before T is aligned and then G's are aligned. So you can combine these multiple sequence, pairwise sequence alignments into a single multiple sequence alignment. It's possible. But if you look at this other example, this is ATG here, A comes first. But if you look at the pairwise sequence alignment between TTT, GGG, and GGG, AAA, this A comes at the second place. Okay, so and between these two things, they are aligned like this. So if you look at these pairwise alignments, how you're going to combine them into a single multiple sequence alignment is not clear. There's conflicting information between these things. Okay, so you have to just disregard some of those pairwise alignments if you want to actually. You can combine these two together. It's possible to combine these two together, right? You can put these G's right underneath here, or combining these two means that putting this AAATTT right here. So A's are going to appear here, T's are going to appear here. So these two alignments can be combined together by putting A's here and T's here. But look at this alignment. This alignment tries to, if T's are here in the other case, this one shows that T's have to be aligned. So this alignment could not be represented in that case. I mean, there's conflicting information here. These 3 sequence alignment, pairwise sequence alignment, you cannot just put them one after another in a row by row and have a single multiple sequence alignment. So there will be conflicting information provided by these pairwise sequence alignments. So that's a problem, which means that vice versa is not true. What is that vice versa? Well, the thing that I want to say is that I told you that pairwise sequence alignments, multiple sequence alignment induces pairwise alignments. So there are induced pairwise alignments here, 28 of them. But if you start with the 28 optimal alignments at first, arriving at a single multiple sequence alignment may not be possible because those pairwise alignments, if you start with optimal pairwise alignments, they may be conflicting with this multiple sequence alignment. So that's why it's difficult to devise an algorithm that starts with pairwise alignments and build this. But all of the heuristics we have these days that are algorithms that are used in practice, they actually start with pairwise alignments and build this multiple sequence alignment by combining them. So they have to have some methodology to resolve these conflicts. We are going to see, for example, something called star alignment. Star alignment will not have any conflict in it because it's going to choose one of the sequences out of the, for example, we have 8 sequences here. If we choose one of the sequences as a pivot sequence or as a reference sequence, which is at the center of star, and instead of using 28 alignments that are possible from here, use the 7 alignments to this. If you choose one pivot sequence, the pairwise alignments to this sequence, alignment of this to this one, this one, this one, and the other four, by using these 7 instead of using 28, if I just use 7 of those alignments, they will, I can, since this one of the sequences is used as a reference, it's like a pivot, it will make sure that those 7 alignments are not in conflict with each other. Okay, so we can directly write those 7 alignments on top of each other. This will give us a multiple sequence alignment. Okay, but the question here is that which one of these sequences am I going to choose as a pivot? Which sequence do you think is going to be a good pivot? I mean, in this specific example on the slide, maybe any of them is a good pivot. But in general, we'll see that a sequence which is close to all the other sequences will be a good pivot, because we are going to be making, when we are doing pairwise, optimal pairwise alignments, when we make a mistake of matching one amino acid to another in that pairwise alignment, that mistake is going to remain in our multiple sequence alignment when we merge them. So if you have, and you're bound to make more errors, mismatches, unmatches, you're bound to make more errors if two sequences are not so similar to each other. But if two sequences, there's a shared similarity between two sequences, and if this similarity is large, for example, when you're aligning two sequences that are 90% similar to each other, the alignment is going to work very nicely. You're going to get good results. But if you're trying to align two sequences that are only 20% similar to each other, the optimized, even if the pairwise sequence alignment gives you the optimum best way to align these two things, it may make errors. It will decide to get a higher score. It will optimally, it will still give you the best optimal score, but biologically the decisions that are made to match certain amino acids with another may be incorrect, and this incorrect alignments may only be realized when you see all of the sequences together. Again, one such example is this Garfield, the fat cat example. Let me show you that. So it's an alignment of some sequence, which is not a biological sequence in this case. So where do I have that? It's all the way to the end, I think. Yeah, here. Again, this is a figure from your textbook. It's an alignment of for multiple sequence alignment of 4 sequences. So we have Garfield, the last fat cat, Garfield, the fast cat, Garfield, the very fast cat, the fat cat. So probably they all evolved from the sentence Garfield, the fat cat, which is not here, right? I mean, the hypothetical ancestor here, which we know, should be Garfield, the fat cat. We know that Garfield is not fast. We know that Garfield is fat, okay? And also, it's not the last fat cat. There are other cats that may be fat and come after Garfield. So usually, I mean, obviously there has been some mutations in our Garfield, the fat cat string. For example, there's an insertion like last, and this last became fast in some mutation. It was, somebody said, for maybe, for example, Garfield, the last fat cat, but that if that you mutate that L to an F, it becomes the Garfield, the fast cat. And there is a deletion. Maybe fat is deleted here, or maybe there's an insertion of if this Garfield the fat cat, maybe an insertion of S here, yeah, Garfield the fast cat, and it became Garfield with just single insertion, Garfield the fat cat become Garfield the fast cat. Now, if you know the hypothetical ancestor, if we had this Garfield the fat cat, we could have used the pairwise alignment of each of these things to these mutated cases and find what really happened. So our goal is to figure out what really happened here, right? But if you look at this, for example, the fat cat and the fast cat, for example, if you try to look at the pairwise alignment between Garfield the fast cat and Garfield the fat cat, you will probably align this to this. But here it tries to align the cats. We basically made some errors, and the reason is that if you start building your alignment, with the pairwise alignment between these two things. Garfield the fast cat, Garfield the last fat cat. Look at this. If you knew that probably there was an insertion here, but this fast is also very similar to last, right? So why not, if you look at the optimum pairwise alignment between these two things, fast and last are aligned with each other. Okay, and if you say that, okay, gaps that appear at the end of the alignment, if you penalize them less like semi-global alignment, you may just have one mismatch here, fat and cat mismatch, and this may be the optimum way to align these two things. Instead of having a 3 gaps here, an exact match, maybe you don't penalize terminal gaps in this pairwise alignment. That may be the case. Okay. Otherwise, if you penalize all gaps equally, I think this is obviously this is not the optimum way to pairwise align these two things, because cat, there's an exact match of cat and cat here. Okay. But obviously, a terminal gap is penalized less compared to a gap that appears in the middle in this example. So it's just as an optimum case. So if you build these pairwise alignments together, and the error that we make remains as we progressively build this alignment, and at the end we may end up with something completely incorrect, bad. So that's the difficult thing about pairwise using pairwise alignments to build a multiple sequence alignment. We make decisions by looking at pairwise things, but if you look at the entire thing, and if you knew the hypothetical, if you knew the ancestor sequence of these two things, it would be a better alignment. But most of the time, if you look at the entire 4 sequences and try to align them, for example, these cats, obviously, they all share one common thing. They're all about cat. So this cat is incorrectly aligned here. But because the fact that in the first sequence, cat was aligned to this fat, therefore we have to introduce this error early in the case. So that's the progressive alignment has this limitation. Once you introduce an error, it's going to remain like that. There are techniques, recent multiple sequence alignment techniques, usually they do certain perturbations. After they obtain the final multiple alignment, they shake the multiple sequence alignment a bit, which means that they do small changes here and there, see whether the alignment score is going to increase overall. For example, in this shaking thing, this cat may move here and you see that it's a better score. And they actually iteratively, these final iterations of these perturbations of the multiple sequence alignment may improve the final score of the multiple sequence alignment. But yeah, this today it was just an introduction to what multiple sequence alignment is and how we are going to have heuristics that start from pairwise alignments to build this multiple sequence alignment. And I'm going to continue talking about multiple sequence alignment on Monday. We'll probably progress a lot more on Monday. We'll have 2 hours of lecture on Monday. And then we're going to continue talking about this the whole next week. We'll see basically heuristics. We are going to see the star alignment in detail, which is choosing a pivot and using the pairwise alignments to this pivot to compute the multiple sequence alignment. Here, obviously, choosing a single pivot is a big limitation of this algorithm. Cluster omega, for example, does not have a single pivot. It uses a hierarchical relationship between hierarchical relationship of these sequences together to guide how these pairwise alignments are going to be connected, combined together to produce the overall alignment. Okay, so that's it from me for today. You can a question on slide 43. Let me directly go. Yeah, 43 is this one, right? Finding the protein, finding the hidden Markov model for a protein family. If this is the correct slide, go ahead and ask your questions. I will be happy to answer. And I will. The first bullet here. Given a set of sequences, can we find the parameters of a hidden Markov model without performing a multiple sequence alignment first? So this is a different problem. It's like if we were given, if you know that a certain number of orthologous sequences, they share the same protein function. We know the domain, but we also know that they share very small sequence similarity. Yeah, in the first bullet, we don't perform an alignment. So that's the thing. Because multiple sequence alignment is a heuristic by itself. It doesn't give us optimum thing. So what if the multiple sequence alignment produces incorrect results? If we have a protein domain with very small sequence similarity, we may actually say that I don't want to do multiple sequence alignment first. But if you already have the multiple sequence alignment, the first bullet doesn't apply to that. We can directly go ahead and use the technique we have learned in class if we are given the multiple sequence alignment. But if we don't have the multiple sequence alignment, it's still possible to build a profile hidden Markov model for these. And the way it's done is this. We start with imagine if we know there are 5 match states. We start with some random transition probabilities between match states and between delete states. And what we do is at each iteration, for example, we compute, if we just start with random transition probabilities, we can, for each of the protein, if each of the members of the protein family, we may compute what is, by using Viterbi, or by using backward and forward algorithm, we can compute what is the likelihood of obtaining this sequence from this random. We start with some random hidden Markov model. We can compute that, right? This Baum-Welch algorithm tries to perturb those transition probabilities in the next iteration such that the probability of observing those members of the protein family, each one of them, the probability is going to increase at every iteration, just like gradient descent, for example. So at every iteration, if I change this transition probability to this, is it going to increase the probability that this family member belongs to this pHMM? So therefore, this Baum-Welch algorithm is a highly iterative algorithm. There is a technique in statistics called expectation maximization. So it tries to maximize the expectation of those, each family member belong to this family every iteration. After it modifies the profile hidden Markov model, it computes the probabilities again, and based on that, it changes again, performs perturbations. So it does this again and again until it converges. The pHM profile hidden Markov model parameters, transition parameters, converge onto something. So we haven't seen that algorithm. So we don't know the Baum-Welch algorithm, but as you can see, it doesn't use it's a completely different technique. It doesn't use the multiple sequence alignment. So yeah. So we can actually build without a given MSA, we can actually build a profile hidden Markov model. But most of the techniques, I think, superfamily database, I think it uses some kind of a sequence alignment to build the pHMM. It doesn't use Baum-Welch as far as I know. But one thing that is interesting is that given a protein family, it uses, when you go to superfamily database, you'll see that for a given protein family, there are more than one pHMMs. Each one is constructed by selecting one family member as a reference. And just like star alignment, it tries to, I think, build multiple sequence alignment by using each one of the family members as reference one by one. So if you go ahead and take a look at the superfamily database, you will see lots of protein pHMMs for a single family, because different versions are built by using each family member as a reference one by one. So it is possible to also construct pHMM without multiple sequence alignment. All right. Any other questions? Let me stop the recording, by the way.